It's my pleasure today to have Steve Rayan with us. Um, so Steve did his master's in mathematics at McGill under Nikki Cameron, um, after which he moved on to Oxford, if I remember, as a Rhodes Scholar.
Commonwealth
Steve,
Scholar.
Commonwealth Scholar. He did a PhD there also in the math department with Nigel Hitchin, working on the geometry of co-Higgs bundles. And after completing his PhD in Oxford, he went back to Canada in Toronto as a postdoc at U of T. He spent 4 years at least at U of T, and we overlapped in Toronto and in Montreal, so I know Steve personally. After his postdoc, he got an assistant professor position at the University of Saskatchewan. He's now an associate professor, so congratulations. And interestingly, he created the Center for Quantum Topology and its application, Quanta. And he's also the director of that center, which brings together people from mathematics, but also physics and other neighboring fields that care about quantum mechanics together, which is a very interesting application. Yeah, I mean, it's my pleasure. And today, Steve will tell us about moduli spaces. And I forget all the details of that, but Steve will tell us more. So Steve, please take over.
Right. Thanks so much, William, for the very kind introduction. Can you hear me okay?
Yes.
Okay, great. And thanks to you and Franck and Guillermo for the invitation. I always love to visit Montreal. I would prefer to, of course, if possible, be there in person, but I'll settle for the virtual platform. I'm just going to share my screen. There we go. So you should see that. And I can't see the chat at the same time. So if there's a question in the chat, if one of the organizers could, feel free to stop me. So this talk is on the geometry and physics of Hitchin systems, which are a type of moduli space, as William said. This is going to be a fairly broad survey. I'm sort of giving this colloquium style, and I'll be, advertising a lot of features of Hitchin systems, and as such, I may not, do justice to a lot of the things that I'm going to mention. It's really just to give, in recognition of the many different interests and backgrounds in the audience, I want to sort of just give you a broad overview. Although I will talk about, or at least advertise some new work at the very end. And, I'm a mathematician, but, recently I've been giving, more talks for physics audiences. And I've decided that one of the main differences between a math talk and a physics talk is that in physics talks, they have pictures of people, which almost never happens in math talks. So I've decided to throw in pictures of, of people who've contributed to this beautiful subject along the way. Okay, so the Hitchin system, the way I like to view it is it's a bridge between geometry, and geometry in many different flavors, differential, symplectic, and algebraic, also representation theory, and physics. And in physics, it mainly appears in two ways, integrable systems, but also it enjoys various connections to high energy physics. I'm going to be talking mostly about the geometry and a little bit about the physics, and maybe less so about the deep connections to representation theory. So I'd say the Hitchin system arose as part of the deep mathematical investigation into gauge theories that began in the late 1970s with people like Atiyah. And in particular, this Hitchin system was discovered, of course, by Hitchin in 1987. Okay, so first picture, here's Nigel Hitchin. And the basic ingredient in defining a Hitchin system is to fix some Riemann surface of genus 2 or larger. Another key ingredient would be to fix a Lie group. Could be can be allowed to be a non-compact Lie group. For us, this will just be mostly GL, but I will talk about other groups a little bit later. Okay, so we fix a Riemann surface, and these are maybe just topological surfaces. I want them to have a complex structure. And as I said, I'll take the genus to be 2 or larger. And just some notation, I'll let 1 here. So if my Riemann surface is X, I'll let 1 stand for the trivial line bundle X cross C. And I'll let T star X stand for the holomorphic cotangent bundle of X. So you can think of the cotangent bundle, but I want holomorphic one forms as its sections. These are both line bundles, but in a complex sense. The fiber here is the complex numbers. Now, a Higgs bundle, this is sort of a main player in this subject. I'll tell you how this connects to Hitchin systems in a short while, but a Higgs bundle is a pair of data. First of all, we fix a holomorphic bundle. It's a smooth bundle with the extra data of a holomorphic structure of rank R. So the fiber looks like CR, and we'll fix its Chern class, regarded as an integer. I'll fix it to be some integer D. And the second piece of data is a holomorphic map phi. This is a map from the bundle to itself, but we would say twisted by the cotangent bundle. So this is like a holomorphic linear map of the bundle to itself, but taking values in one forms. Now, another piece of notation that's important here is that I want to have a notation for the global sections or the global holomorphic sections of some bundle. So if my bundle is F, I will use H naught with the superscript to denote the holomorphic global sections. I mean, you might use gamma, but I would usually use that for smooth sections. So this has a little bit more of a restriction. Once I have that notation in place, then I can think of this map phi as a global section. It's a global map on the Riemann surface that's an endomorphism of E, a map from E to itself, again tensor by the cotangent bundle. And endomorphisms of E I can think of as E dual tensor E, and that point of view is important a little bit later on. And this object phi is what we call the Higgs field. And in this formulation, it need not be a scalar field because the rank of the bundle may be bigger than 1. So that's an important distinction here, maybe on the mathematics side. Now, the simplest example of a Higgs bundle is to take E to be simply a line bundle L. Again, this is a holomorphic line bundle, so its fibers are really two-dimensional over R, but everything here is complex. And theta here, the Higgs field, will just be a holomorphic one form on X, because a map from a line bundle to itself, a global map from a line bundle itself is just a scalar, and so we only see the one form part. Another way to say that is that end L is L dual tensor L, which is just the trivial line bundle, and so that goes away, and we're just left with the cotangent bundle part. Now, a popular example of a Higgs bundle of higher rank, so a less trivial example, so this is rank 2, is to take the direct sum of the trivial line bundle and the cotangent bundle, and to have a Higgs field, which is a 2 by 2 matrix with a 1 in one corner and something else in the opposite corner on the anti-diagonal. So the 1 here is going from T star to 1, but then tensor T star. So that's from T star to itself. I can just take that map to be the identity. The other map is going from 1 to T star, tensor T star. So this is actually a quadratic differential, like a sort of square of a one form locally, if you like. So this is a popular example. It connects to uniformization Riemann surfaces. Now, what I want to do is consider Higgs bundles in the following way. Rather than start with a holomorphic bundle, I want to start with a smooth rank R bundle, which is Hermitian. So it has a Hermitian metric on its fibers. And again, I'll fix the Chern class to be D. And then I want to consider the following equations. So on the bundle E, I want to put a unitary connection, so it's compatible with the Hermitian metric. So this first equation here, I'm looking at the, let's say, the trace-free part of the curvature of this connection. And I'm going to add a similar object to it, which is the commutator of phi with its adjoint under the Hermitian metric. And I can ask for this to be 0. So that defines the first equation. And in the second equation, I'm going to look at the, if you like, the 0, 1 part of the connection. And I want to look for Higgs fields phi. So these are, if you like, smooth Higgs field phi. So these are acting on the smooth bundle E, but much in the same way as the holomorphic version. And I want phi to be in the kernel of this d bar operator. So I'm asking for, what I'm in a sense asking is for phi to be holomorphic. Why? Because this unitary connection on this Hermitian bundle, that gives the bundle a holomorphic, or if you like, a complex structure. And the second equation is asking for phi to be holomorphic with respect to that structure on E induced by A. This pair of equations is known as the Hitchin equations. They're a dimensionally reduced version of the self-dual Yang-Mills equations from R4. So we impose self-duality under the Hodge star, and we ask for solutions that are spatially independent with regards to one spatial direction and time independent. And then you're left with equations with a conformal structure on a Riemann surface. And these are the Hitchin equations. And I want to consider the space of gauge equivalent solutions of these equations. I'm going to give that space a notation, X to remember our choice of Riemann surface, and R and D to remember the invariance of the bundle, and M, I can just refer to this as M, and X, R, and D as necessary. Now, the key point here is that every solution gives rise to a Higgs bundle because, again, the unitary connection puts a holomorphic structure on the bundle, so I have a holomorphic bundle, and the second equation is telling me that phi is holomorphic. And so we get exactly the data that you saw on the preceding slide. For r equal to 2, these equations were studied by Hitchin, and then these are generalized to more general R and even more general types of complex manifolds by Simpson. So here's an action shot of Carlos Simpson, and he seems to be pointing to exactly a Higgs field. Okay, so that's a very relevant image. Now, the converse question is interesting. When does a Higgs bundle E phi give rise to a solution of the equation? So I want to reconstruct a unitary connection A and a Higgs field phi, and I put a tilde here because this may not be exactly the same Higgs field on the nose. It could be in the same gauge orbit as the original phi. And implicit here, I need to also reconstruct a Hermitian metric on E. That's a very important part of the data. So you could really think of this as a triple, if you like. Well, it turns out, a very big theorem here that I'm not going to do any justice to, is that a Higgs bundle, if you like, solves the Hitchin equations when for each subbundle of E, so each holomorphic subbundle, and I mean not the 0 subbundle and not the whole bundle itself, but every proper subbundle. So when I look at every proper subbundle that is invariant under the Higgs field, this means, if you like, roughly the same thing as in linear algebra. So I'm looking at subbundles U that are mapped into themselves by phi, but you have to accept that there's always going to be the twist by T star. So let's look at proper invariant subbundles of E. And if they satisfy this inequality, that the Chern class of the subbundle over the rank of the subbundle is less than or equal to the first Chern class of E over its rank, which, remember, this is D over R. If we always have this, well, then we call E phi semi-stable. And this is exactly a solution, or admits a solution, if you like, of the Hitchin equations. You could say that the term stability here is because we're really looking for things that are in the zero locus of this first expressions. They're energy minimizers, if you like, for this functional. And the semi here is the case where we're allowing the equality. Stability in the strict sense is when we don't have the equality. So this is a theorem originally due to Hitchin. And, you know, for example, the example that I showed you earlier with the 1 plus t star and the 2 by 2 anti-diagonal matrix, this is stable, if you like, for the reason that there are no proper invariant subbundles. T star is being mapped to this side, 1 is being mapped to that side, so there's really nothing to check here. And that means that it automatically admits a solution of the equations for rank equal to 2. And the degree here actually happens to be 2g minus 2, where g is the genus of the Riemann surface. This is a very powerful point of view because it's, you know, once you have this theorem in place, it reduces the problem in a sense to linear algebra. We're talking about families and invariant subspaces. And intersection theory, because I need to, you know, compute Chern classes of things. Well, this theorem is also telling us that there's an equivalence between two moduli spaces. So I would define the Hitchin system to be the moduli space of Higgs bundles taken up to isomorphism, or maybe I should say the moduli space of semi-stable Higgs bundles. And that is equivalently, by the theorem that we just mentioned, the space of solutions to the Hitchin equations up to gauge equivalence. And so this is a single moduli space which I can view in an algebraic way, or if you like, in a more differential geometric or gauge theoretic way. And the correspondence between these 2 points of view is sometimes referred to as a Hitchin-Kobayashi correspondence. And just as an aside, and Will and I were sort of speaking about moduli spaces before this talk. And you know, Riemann, you know, coined the term moduli back in 1857 to describe, you know, the set of all Riemann surfaces of a particular genus G, which today is on a different footing as a more firm footing as maybe the moduli space of curves. And in high energy physics, people often refer to the moduli of vacua. That's a moduli space in a particular sense. But, you know, moduli space is really just any sort of space that is keeping track of objects up to isomorphism. Now, I want to introduce another very closely related moduli space from which you can see the moduli space of Higgs bundles, or equivalently the Hitchin system, arising in a very natural, purely mathematical, geometric way. So I want to, you know, we used M for the Hitchin system, the moduli space of Higgs bundles. I want to use U to represent the moduli space of holomorphic bundles on our Riemann surface X. Just bundles. So if you like, I'm taking phi to be 0. And again, I'm fixing a rank and a first Chern class. Now there's a stability condition as well. I mean, the natural thing to do, you know, is to forget about the Higgs field. So I forget about things that are phi invariant, and I look at all proper subbundles of E. And if you like, that's consistent with the point of view of taking phi equal to 0. You know, everything is invariant under the 0 map. You can ask the question now, you know, having done this, are my just bundles alone, are they solutions of some equations? And it is. I mean, I can just take the, you know, the second Hitchin equation just goes away completely, and half of the first Hitchin equation goes away, and I'm just looking at flat unitary connections. Okay? And so the equivalence here between holomorphic bundles and flat unitary connections, this is an earlier correspondence due to Narasimhan and Seshadri. Here is Narasimhan. Now, I could ask a very basic question about this moduli space of stable or semi-stable holomorphic bundles. What is the tangent space to this moduli space at some bundle? That's an isomorphism class of bundles. And this has the virtue, if we can answer that, it would also tell us the dimension of the moduli space. Well, I guess, literally speaking, the answer is to differentiate the bundle in an appropriate sense. I want to understand first order deformations of the bundle. And so that's really saying that the tangent space at E to the moduli space of bundles is, it's a cohomology group, if you like. It's H1, so we used H0 for global sections. H1 means things that are defined on twofold intersections, and that's exactly what the data of a bundle is. A vector bundle on say a Riemann surface like X is locally defined on twofold intersections, and the data supported on those twofold intersections, of course, are transition functions, which are invertible matrix valued functions defined on those intersections. And if I'm going to deform to first order, that's really I'm going to add a matrix to that non-vanishing or if you like invertible matrix valued function. So if you like, the deformation of the bundle is an object in cohomology that lives here. And just thinking of ND as matrices. Well, we don't, why work locally if you can work globally? So if we want to go back to global things, the answer is to integrate and use Serre duality. And Serre duality says that we can go back to H0, global things, at the cost of twisting by the dualizing bundle, which happens to be the cotangent bundle. Well, there's two observations here. We took the dual of the tangent space, so that means we must have now the cotangent space to the moduli space of bundles, but also this twisting by T star, well, this is exactly the space of Higgs fields phi for our bundle E. And so the cotangent directions in the moduli space of stable bundles are precisely the Higgs fields for E. And so you might be tempted to conclude from that if I take the moduli space of bundles, this is an honest space on its own, and I want its cotangent bundle, you might be tempted to conclude is the moduli space of Higgs bundles, because the cotangent spaces are spaces of Higgs fields. And that's almost true. There are things actually so the cotangent bundle to the moduli space of bundles is contained inside the moduli space of Higgs bundles. But there are some things in here that are not in the cotangent bundle, because there are some stable Higgs bundles whose underlying bundle is unstable. It's stable as a Higgs bundle. It has bad subbundles that are filtered out by the Higgs field, but the vector bundle on its own, if I try to check stability, it will not be stable. And so there isn't a global projection back to the moduli space of stable bundles. However, this containment of T star U in M is open dense. Now, using Riemann rock and the information on the previous slide, we can work out that the dimension of the cotangent space, and so the dimension of the moduli space of bundles, is actually r squared times g minus 1 plus 1, where g is the genus of the Riemann surface. And remember, r is the rank in our problem. And then because of this open dense containment, we simply double this, and now we have the complex dimension of the moduli space of Higgs bundles, or if you like, the Hitchin system. And as a real number, this is divisible by 4, which is actually a very important fact, and that will come back later in our discussion. So this is one way to almost view the Hitchin system as a bundle, but there's another way we could try to do that. So thinking again, linear algebra is our friend. In a generalized sense, we can say that phi has a characteristic polynomial. It's just a global object now, rather than just a sort of local one for matrices. And the zero locus of this characteristic polynomial, it's not just a set of eigenvalues anymore. It's a set of eigenvalues for every point in X. And this now is a Riemann surface of its own. So this is referred to as the spectral curve for obvious reasons. It's really the spectrum of phi. And because phi is a T-star valued object, really the eigenvalues can be thought of as one forms. And so the spectral curve determined by solving the characteristic polynomial of phi embeds in the total space of the cotangent bundle on X. And it turns out that there's a whole, if you like, torus's worth of Higgs bundles that share the same spectral curve. This torus is related to the spectral curve in that it's the Jacobian of it. So that's actually the moduli space of line bundles on the spectral curve. And so what this is telling us is that, I can take the space of all possible characteristic polynomials, and that the moduli space of Higgs bundles is a torus fibration over that space. For each characteristic polynomial, there's a spectral curve. That spectral curve gives a torus. But some of these tori are degenerate. If I choose a sort of a bad spectral curve or a sort of bad characteristic polynomial. And it turns out that every such torus is compact, even the bad ones. And the proof of this, again, is it goes back to Hitchin. And this is a sort of application of the Uhlenbeck-Yau weak compactness theorem. So Yau, as many of you know, is a fields medalist. Here's Karen Uhlenbeck, who won the 2019 Abel Prize in mathematics. So here's a cartoon, if you like, just to be somewhat visual about it. Here's a cartoon, if you like, of the Hitchin system. You can think of this flat space, this sort of affine space, as the space of all possible characteristic polynomials, and then these vertical directions are the tori. So this torus here would be all of the Higgs bundles that share a particular characteristic polynomial. And again, there are some degenerate fibers in this family. By the way, pretty good affine space is Saskatchewan. So it's a cartoon of different version of the cartoon. So it's pretty flat as far as the Earth goes. Okay, so shifting gears slightly, in that exercise with the moduli space of just bundles tells us a lot about the structure geometrically about the moduli space of Higgs bundles, but maybe some finer information, and which takes us back to the physics a little bit, is to study a bit of the symplectic geometry here. So it's a sort of another layer of what's happening. The fact that the Higgs bundle moduli space is almost the cotangent bundle to the moduli space of bundles, well, there's a preferred symplectic form here, which of course gives us a Poisson bracket, and that actually extends to the whole of the moduli space of Higgs bundles. It extends over this small locus that happens to not be in this cotangent bundle. And it turns out that the characteristic coefficients, literally the coefficients of the characteristic polynomial of phi, we can take their real and imaginary parts if you like. These are algebraically independent Poisson commuting functions with respect to this symplectic form on the total space of the fibration structure on this moduli space. In fact, these tori, if you like, are the Liouville tori of the dynamical system. So that's what I'm saying is that there is a dynamical system structure on the moduli space of Higgs bundles, and that's in fact why we call it the Hitchin system. So this result, goes back again to Hitchin, but others, including A.L. Markman in '94. There's also Bottichin in '95. And so the theorem of Hitchin is that the moduli space of Higgs bundles is an algebraically completely integrable Hamiltonian system with explicit Hamiltonians, which you can compute from the Higgs fields directly. So the Hitchin system, again, is a genus 2 or larger phenomenon. I mean, it's not new, of course, to have the involvement of Riemann surface theory in integrable systems. So as a genus 2 or higher phenomena, the Hitchin system reveals, if you like, new integrable systems of KdV or Kp type. As I already said, the Liouville tori of the dynamical system are presented through the spectra of the Higgs fields. And there's, if you like, a lax pair phenomenon here. The time evolution of a Higgs field along one of these tori is given by a lax pair equation. And in sort of low rank and low genus, you can sort of compute the lax partner. And it's like I know that this can be explicitly done in very low genus. If you adapt the Hitchin system in certain ways so that it makes sense in genus 0 or genus 1. So either by, instead of twisting by T star, twisting by a line bundle with higher Chern class, or by puncturing the curve, then you can, then two things happen. You can compute this lax partner explicitly. You can also relate the Hitchin system to explicit known classical integrable systems, like those coming from Nahm's equations. You can define that on P1 by twisting by the tangent bundle instead of the cotangent bundle, and also geodesic flow on the ellipsoid. And I'd say a folklore belief is that all integrable systems in nature are somehow related to the Hitchin system, some instance, limit, or modification of the Hitchin system, and that's been an impetus for much research. Now, the fact that this integrable system structure exists on the modular space of Higgs bundles leads to questions about existence of action angle coordinates, of tau functions. Can you quantize the Hitchin system? These are reasonable and interesting questions. The Hitchin system can also be regarded, because there's a massive family of spectral curves at play here. The Hitchin base is parametrizing, a large family of spectral curves. So this is actually a natural setting in which place what's called topological recursion unfolds. I'm referring to the topological recursion of Chekhov, Eynard, and Orantin, although it's also connected to the topological recursion of Mirzahani. And so this connects the Hitchin equations to WKB analysis. So there, in all of these questions, have been explored over many years, either implicitly or explicitly in the works of many people. And there's Jorn Andersen, David Bravia, Marco Bertola, Indranil Biswas, Philip Bolch, there's Bouchard, Dumitrescu, Eynard, Harnad, Hurtubise, Korotkin, Malazi, Previato. There's also, especially in the quantization, there's Balens and Drinfeld. So there's a very large body of work that's appeared here over many years. And the question of the integrability of the Hitchin system, it's sort of been realized that it's closely related to other integrable systems that have appeared in mathematical physics, in particular the Nakajima quiver varieties. So this is sort of work that's emerged, myself and others, Jonathan Fisher and Laura Shaposnik, in a sort of emerging series of papers. What's good about this is that a quiver is a directed graph, and it due to work of Nakajima, is connected to earlier work of Kronheimer. From a directed graph you can produce an integrable system. An integrable system has sort of many features that on the surface seem related to the Hitchin system. However, the Nakajima quiver varieties, because they just come from a graph, is purely finite dimensional analog of the Hitchin system. Whereas the Hitchin system, at the end of the day, is finite dimensional, but it's infinite dimensional in the sense that it's the quotient of an infinite dimensional space of connections via a gauge group. And then what results from that quotient happens to be finite dimensional, where Nakajima quiver varieties were always finite dimensional. And so the connection between these two different systems is made precise in my work with Fisher and Shaposnik. Now, you should see this, view this talk as really as an advertisement for the many deep features of the Hitchin system. No matter how much time I spend with moduli of Higgs bundles, I'm always fascinated by how many different geometric, features occur at once. Another selling point of this moduli space is Hyperkahler geometry. So it turns out that the moduli space of Higgs bundles has a trio of quaternionically commuting complex structures. So there are, if you like, quaternions defined on the moduli space, traditionally call them I, J, and K, and they're covariant constant along a common metric H, which we call the Hitchin metric, which arises via Kahler reduction. And what you can do is, this is first of all called a Hyperkahler structure. So it's 3 Kahler structures at once. And as with any individual Kahler structure, what I could do is I could use any of these 3 complex structures to anti-symmetrize the metric, thereby producing 3 respective symplectic forms, omega I, omega J, and omega K. And the integrability, the integrable system that we were speaking of is the one coming from the I complex structure. And putting emphasis on the I complex structure, that's the one that should morally be called the moduli space of Higgs bundles. But what I can do is I can, we call it Hyperkahler rotation. I can Hyperkahler rotate to J or K. And that, more honestly, has an interpretation as a moduli space of flat, irreducible, let's say GLRC connections, or if you like, irreducible GLRC representations of the fundamental group of X. And I put just as a proviso here when the rank and degree in the problem are co-prime. If they're not co-prime, then I would have to change a few of the adjectives here. So I just wanted to go for simplicity. And when R and D are co-prime, then that excludes the semi-stable case, and I just have stable Higgs bundles in the moduli space. Now, the Higgs bundle moduli space, so I is a different complex structure than J and K. They are not isomorphic in any sense. But the underlying smooth structure here, there's a diffeomorphism. So the moduli space of Higgs bundles and the moduli space of flat connections, these are diffeomorphic, and this is called non-abelian Hodge theory. This is sort of a theorem built up by Hitchin, Donaldson, Corlett, and Simpson. And you can see this as a non-unitary extension of Narasimhan-Seshadri. Narasimhan-Seshadri was saying that there was a diffeomorphism between a moduli space of flat, irreducible, unitary connections and just a moduli space of ordinary holomorphic bundles. And this is Kevin Corlett, one of the architects of non-abelian Hodge theory. And this beautiful Hyperkahler structure, one thing that it tells us is that the moduli space of Higgs bundles is a Calabi-Yau manifold. So the quaternionic holonomy of the moduli space of Higgs bundles, by virtue of being Hyperkahler, means that its holonomy is contained in SUN. It's just one of many different equivalent ways of saying that that this is Calabi-Yau. So there's a complex Kahler Ricci flat metric on the moduli space of Higgs bundles, and that's the metric H that we mentioned earlier. But the proviso again here is that this is non-compact, whereas people are, at least traditionally, were interested in compact Calabi-Yau manifolds in string theory. But if the main feature of Calabi-Yau manifolds, again from the point of view of high energy physics, is whether they have mirror symmetry, we can ask that question about the Hitchin system. And the proper setting for this discussion is to think of G bundles. As I said, we've been considering GLR everywhere, but we need to sort of just stand back for a moment and think about G bundles. And most of the prior discussion carries over just fine. It turns out that the question of mirror symmetry is well defined, and the mirror of the moduli space of, let's say, principal G Higgs bundles on a Riemann surface happens to be the moduli space of principal LG Higgs bundles, where LG is the Langlands dual group. So this is, again, work borne out in several papers. There's Hausel-Thaddeus, Kapustin-Witten, and Donaghy-Pantev between sort of 2003 and 2012. And the Langlands dual group being, group you get from G by swapping characters and co-characters. Just as an example, if I take SLRC as my group, then its Langlands dual is PGLRC. And what happens is that the two bases, the two Hitchin bases of, if you like, invariant polynomials associated to the Higgs field for G and LG can be identified. And then what happens is that the mirror symmetry is mapping tori in one moduli space to their dual counterparts in the other. And this is, if you like, consistent with Strominger-Yau-Zaslow or T-duality form of mirror symmetry. But you can go back to the beginnings of mirror symmetry and ask if there is an equivalence of Hodge numbers or between these two spaces. And you can refer to that as a topological test for mirror symmetry. And this has been a long program carried out, from, I guess, in the 90s, but I guess, framed in terms of mirror symmetry with the work of Hausel and Thaddeus, and was completed recently by Michael Grochenig, who's at the University of Toronto, and his collaborators in 2017. This is one part of this subject where I've spent much of my time interacting with Hitchin systems, studying the topology of Hitchin systems, computing numerical topological invariants of various flavors of this moduli space. And in all of these flavors, the principal tool for studying the topology is the C-star action. So the moduli space of Higgs bundles comes with a rescaling action. I can rescale phi by some non-zero complex number t. Of course, if you're working at the level of the Hitchin equations, you might want to replace this with a U1 action. That will preserve the level sets of the Hitchin equations. If you're working algebraically, then you can just take C star. The point is that the fixed point locus of the C star action encodes the rational singular cohomology of the moduli space. So by computing the fixed points, you can determine everything about the cohomology of the moduli space, and therefore extract Hodge numbers and Bethe numbers and related topological invariants. This is a very hard question in a sense. The connected components of the fixed point locus are positive dimensional. They are not isolated fixed points. And so you're not, what that means is you're not just summing over Morse indices. You have to then compute the topology of the individual fixed point components. And they happen to be quiver varieties. So to each component, there's a quiver, a graph, which determines its structure, but not in any simple way. These are not quiver varieties in the ordinary sense. They're quiver varieties in a category of bundles, as opposed to the usual thing, which would be to label nodes by vector spaces. And so this is a very interesting problem, and it leads to contact again with representation theory through quiver varieties, but also with combinatorics. The cohomology ring of the modular space of Higgs bundles is full of combinatorial identities that are sort of, you can, if you like, use the geometry and the topology of the moduli space to make combinatorial conjectures. Certain things that you know have to be true geometrically force, thrust upon you certain realities in the cohomology ring, which then become various kinds of identities involving Bethe numbers, which then become their own combinatorial statements. If you're interested in this, then you can see more about the topology and combinatorics in relation to quivers, in the context of Hitchin systems, in a survey paper that I wrote here, which is available on the archive. Now, sticking with the elements of the Hyperkahler structure, this Calabi-Yau metric H, the Hitchin metric, has been conjectured recently by physicists Gaiato, Moore, and Knightsky to be a solution of a particular integral equation coming from a certain path integral formulation. And by studying this formulation perturbatively, they see that the Hitchin metric is related to a simpler Hyperkahler metric, the so-called semi-flat metric, which appears in the work of Dan Fried and others. This is a metric that you can define on the total space of an integrable system. So it's related to the special Kahler geometry of an integrable system. So the Hitchin metric is equal to the semi-flat metric plus some corrections that die exponentially, some so-called instanton corrections. And this relationship is only defined away from the, if you like, the bad fibers of the Hitchin system. The semi-flat metric is undefined there, yet the Hitchin metric persists. The Hitchin metric is defined on the entire moduli space. So you can think of the Hitchin metric as a correction to the semi-flat metric that allows it to exist everywhere on the moduli space. What's intriguing about this is that the semi-flat metric is essentially explicit. It can be written in terms of the integration of periods for spectral curves. Spectral curves have periods that describe their deformations, if you like, period matrices, and you can write the semi-flat metric in terms of those. I guess to this day, it would be fair to say that no one has written down on a compact Calabi-Yau manifold a non-trivial Calabi-Yau metric explicitly. For these non-compact ones, you can, this is an example where you can almost write down the metric explicitly. So it just, the Hitchin metric is not too far away from the semi-flat metric. And this conjecture has been proven in low rank, especially rank 2, since 2014 in a series of papers by Mazzeo, Svoboda, Weiss-Witt, Fredrickson, and then Dumas, Knightsky. So here's a photo. This was taken at a workshop on Hitchin systems in Heidelberg on a rainy day in 2016. And all of the people except for one that I mentioned on the prior slide are in this photo. In particular, in the front row, we have Andy Knightsky, Laura Fredrickson, and Rafe Mazzeo. So just as a summary, not the end of the talk, but as a summary, the Hitchin system is many things. It's a solution space to gauge theoretic equations that come from self-dual Yang-Mills. It's a completely integrable dynamical system that captures various known classical systems. It's a Calabi-Yau manifold with a nearly explicit Ricci-flat metric. And it has a well-defined mirror symmetry in the physics sense, but which is intertwined with Langlands duality. There's so much here, but you could still ask, is there more? And apart from the various high energy connections, mirror symmetry and string theory, you could ask about the sort of other end of the scale. Are there connections between Hitchin systems and condensed matter? And that's, just in the last few minutes, I just want to give you a sense of some work that's ongoing and very, very recent work. So for those of you who might be interested in topological materials and topological insulators, one very reductionist point of view, standing back from a topological insulator as a mathematician, a point of view would be that, such a material is really a genus 1 surface together with a finite rank Hilbert bundle defined on that surface and a Hamiltonian that acts on that bundle. The key here to understanding the material is its band structure, and this is encoded in the ramification of the spectrum of phi. So phi, if you like, has spectral data, and that forms sheets over our topological surface, and that forms a branched cover of X. And the way in which this branches tells you, if I look at the electrochemical potential and how that compares, or if you like the Fermi level and how that compares to the branching, I can say whether this is an insulator or not. Well, on a torus, the cotangent bundle is trivial. And so this, this data of E and phi looks awfully like maybe a real Higgs bundle with a particular symmetry that makes it a bona fide Hamiltonian. It also, gives us the question of, well, are there topological materials for other genera? And the key here is to look at a Schrodinger equation. What would you do in the genus 1 or the Euclidean case? You would look at a Schrodinger equation with a potential and boundary conditions adapted just to a normal, let's say, Euclidean lattice, let's say in dimension 2 on R2. And that's where your torus is coming from. Well, the key here is to use a potential and boundary conditions adapted to a 4G-gon tessellation of the hyperbolic plane. And here delta is the hyperbolic Laplacian, so the Laplace-Beltrami operator. And yes, again, so this generalizes the way in which we did this in sort of Euclidean lattice to get an ordinary topological material. The key here maybe is to understand that the tessellation has a Fuchsian group gamma, which is non-commutative. So there's a sort of non-commutative hurdle to go to get over, whereas in the Euclidean case everything was abelian. Well, the solutions to this particular equation on hyperbolic space include very nicely behaved wave functions, psi, wave functions that are automorphic with respect to this tiling. So these are wave functions that obey this kind of symmetry, where lowercase gamma here is an element of the Fuchsian group, if you like, a translation of the tiling. So when I translate, what we do is we pick up a factor here, chi, and this is really, if you like, a unitary factor of automorphy. This is a character, if you like, for the fundamental group of the Riemann surface that we get by taking the hyperbolic plane and modding out by gamma. So this is a U1 valued character. And so we can keep track of these characters. And really what we're getting are, we're getting the Jacobian of this genus G curve. So if I take G equal to 2 and I have an 8-gonal tessellation of the hyperbolic plane, I will get a genus 2 Riemann surface. And these characters are giving me points, if you like, in the Jacobian of that genus 2 surface. So here's a picture of an octagonal tiling. I cannot tile the Euclidean plane this way, but I can tile the hyperbolic plane. And this tiling is Poincaré regular. And if I, again, I can identify the sides of this in a particular way and produce my genus 2 surface. Right? What we are saying here is valid for any G. So the Jacobian here, this 2G dimensional real torus, plays the role of a space of hyperbolic crystal momenta in the usual topological band theory. And this is properly the analog of the genus 1 surface. So if you like, there's a real space, which is a genus G curve, and there's a momentum space, which is its Jacobian. So the overall picture here is what we call hyperbolic band theory. And this is very recent work that's I wrote jointly with Joseph Micheko at the University of Alberta. It's in the Theoretical Physics Institute. Hyperbolic materials have actually been synthesized recently, artificially. So by Alicia Kohler and her group, but they remark in their paper that there's no corresponding band theory. And that's what our work provides. But there's a hint of a much larger picture here, because really what we're saying is that the hyperbolic crystal momenta form a rank 1 Hitchin system on a genus G curve. And higher rank systems are possible if we consider Schrodinger equations with non-unitary automorphy conditions. So higher rank and non-unitary, and then we get not just, if you like, line bundles or U1 characters, but we start to get higher rank bundles with Higgs fields. So this is an exciting sort of intersection between Hitchin systems and condensed matter. And in our paper, I just want to remark that we looked at particular higher genus Riemann surfaces. For instance, the Boltzmann surface, which is the most regular genus 2 surface, and we computed its band structure numerically in our paper. And if I've sold you on Higgs bundles, if you think they're as interesting as I do, then you can always buy a Hitchin system. So these are, I don't make any money off of this. These were printed by or designed by Tomasz Hausel, one of the people I referred to earlier. So this is a moduli space of Higgs bundles, referred to as the toy model. This is rank 2 on the Riemann sphere with 4 punctures, and this is a particular 3-dimensional slice that's been 3D printed. So you can get this in various colors. Again, I have nothing to do with this. I don't make any profit, this is quite expensive in Canadian dollars, at least at the time that I printed these, or at least took these screenshots. So I think they've gone down, and this finish is a lot cheaper than the others. But if you want to have a Higgs bundle, if you want to have a Hitchin system on your desk, just go to shapeways.com. Just thought I'd throw that in, because why not? And that's my talk. So thank you very much for listening.
Well, thank you, Steve, for a very nice talk. You covered a lot. So yeah, I can applaud Steve for a very nice presentation.
Thanks.